midterm exam, so
Yeah, he just called me and he said that I also had the same thing. I had my exams and
okay, sir.
just got finished at 6:30. Fine. So are the slides visible
Yes, sir, this is visible.
and the flow is there?
Yes, sir. Flow is there.
Okay, fine.
Over to you, sir. Thank you.
Yeah, thank you. Yeah, good evening, everyone. Myself, PM Pradhan from IIT Roorkee. So in today's talk, I will be discussing regarding a criterion which is called as divergence criterion, and how that is helpful in adaptive filtering. So in general, when we look at the adaptive systems, we do have different kinds of applications. For example, we look at adaptive system identification, adaptive channel equalization, adaptive noise cancellation, and there are many applications. And when we look at all those applications, one of the terms that we normally come across is called as convergence of the algorithm, right? And we see we try to select an algorithm which converges faster, or we look at the convergence rate of the algorithm, or we look at the computational complexity of the algorithm as well as the convergence. Okay. So in today's talk, I'll be touching upon something called as divergence criterion and how that is helping us in convergence of the algorithm. Okay, so the terms are the terms are opposite to each other. In one way, we are talking about divergence, and the other way we are talking about convergence of the algorithm. Okay, so we'll see how these terms are connected to each other: the divergence criterion and the convergence of the algorithm. Okay. So to start with, this is a basic overview of adaptive filtering, right? And we can see in the block diagram that we have some input signal X, and we have some desired signal D. Okay, and we have an adaptive filter through which the input signal X passes through. We get an output signal Y, which is subtracted from the desired signal D, and we get the error signal E. And we use this error signal to update the adaptive filter using some kind of algorithm. There are lots of algorithms which can be used to update the filter weights. The filter weights are nothing but a set of multipliers or weights which needs to be tuned based on some criterion. And the conventional criterion that most of you might have heard about is called as mean square error, or some terms related to the error. So you want to minimize the error. It could be error square, it could be any function of error, but effectively we want to reduce the error that is there as E, and we want our output signal Y to be as close as possible to the desired signal D. So that is the major motivation behind your adaptive filtering. The key applications of adaptive filtering is listed as system identification, noise filtering, adaptive line enhancement, sensor modeling, etc. So I will show you a few applications down the line uh, where we have used the divergence criterion for solving this adaptive filtering problem. Okay, and the applications are no, the listed applications are few in number. There are many more applications of adaptive filtering which have not been listed here. So when we look at these adaptive signal processing or adaptive filtering problem, we look at some kind of cost function. So when I say cost function, the conventional cost function that normally we come across is called as mean square error. So effectively, we want to reduce the error between the desired and what is estimated, that is y of t, and the desired signal is d of t. Okay, but to start with, we could have designed some function of error, not necessarily mean square error. Okay. So, for example, if you look at the absolute value of error, let's say instead of mod dt minus yt mod square, we could have gone for mod of dt minus yt, which is nothing but mod of the error function. But then, since you are going to use this as a cost function down the line, and you want to reduce the error, so effectively you want to minimize the cost function that you have designed. So the problem with designing the cost function as a mod of ET, which is absolute value of error function, is that when you take the derivative of an absolute function, you'll get a discontinuous signum function. So that is the problem with the absolute value of errors. Okay, so that is the reason that we do not use absolute value of error as a cost function. So the no, the next norm that we can come across is nothing but your error square. Okay, of course you can go for error cube, error to the power 4, right? So all other higher order movements of your error. But the problem is, once you increase the order of the error function, that means when you take the derivative, you will have much more complex terms to calculate than the second order scenario. Okay. So that is the reason that preferably we go for error square, where if you take the derivative, then you get the two times of the error function into derivative of the error with respect to the weight. Okay, so that is the reason that we prefer to go ahead with error square as a cost function. And expectation is because these when you start any adaptive filtering process, you start from certain random weights. So it's not necessary that the initial weight that you assign to the adaptive filter is very close to the optimum solution or very far away from the optimum solution. It's so every time you generate the initial weights, it could be any value. So that is the reason that since it's a random random assignment of weights, so what we do is effectively we want to perform multiple experiments, Monte Carlo experiments, and then we take the average over those Monte Carlo experiments. So that's the reason that you have a cost function, which is expected value of error square. The most popular algorithm that you come across while using adaptive filtering is the least mean squares algorithm. And the term itself indicates that the third term is your squares. So effectively that is square error, which is shown that, and mean is value which is again shown in J of H term. And least is you want to minimize this error square cost function. So effectively the algorithm is the interest in designing this LMS algorithm was to minimize the mean square error while making sure that the filter coefficients approach the optimal weights. Now, that was the conventional scenario. Now, there are some challenges when you use mean square error as a cost function. Okay. For example, let's say the first challenge is your sensitivity to outliers. Now, no, for example, let's say you got a desired value which is very high as compared to the normal signal values. Let's say the normal values are, let's say, between 0 to 1, and let's say you got one of the values in between as 4 or 5 or 10. So those values act as outliers. So those are very far away from the from the range of the input that you are expecting for this application, right? So the outliers are quantified based on the standard deviation term. Okay. But since the value is a very high value, what would happen is when you calculate the error as desired minus estimated one, so your error would be a very high value because your desired is now a very high value. Okay. So that is the reason that your error is a high value and error square becomes a very high value. Okay. So that is the reason that if you have an outlier in the signal, then the mean square error will give rise to a very high value of error at that instant. Okay. So this is very sensitive to outliers. So this cost function of mean square error, error square, is very sensitive to outliers. Okay. The second challenge with mean square error is the poor robustness in non-Gaussian noise. Now, when you look at no, when you look at the distributions, you'll see that most of the cases, the assumption is that my noise is Gaussian in nature, or my input is uniformly distributed or Gaussian distributed. These are the typical two distributions that we use, and in general for noise we use Gaussian distribution. But it's not necessary that the noise that is being observed in the system is Gaussian in nature. There are lots of applications where you see Laplacian noise being analyzed, being observed at the receiver end. Okay, so in those scenarios, your error square cost function will give poor performance. Okay, so that is the reason it has very poor robustness as far as the non-Gaussian noise is concerned. Okay. Similarly, the third challenge is limited convergence in correlated noise. Now, when we say that the conventional adaptive filtering is used for certain application, the conventional assumption is the noise that we are going to face is a Gaussian noise, and those are uncorrelated noise. So, additive wide Gaussian noise, AWGN, is the general term that we use for conventional systems. Now, in those scenarios, what happens is all the noise samples are uncorrelated to each other. But it's again not necessary that every system will face uncorrelated noise. There are systems where there are non-stationary environments where you, when you record the noise, you will see that the noise is correlated to, the noise samples are correlated to each other. Okay. So in those scenarios, you will see that the mean square error as a cost function will have limited convergence. The fourth one is suboptimal performance in multimodal distributions. Means if the cost function, if the system has a single minima, a single global minima, or a single global maxima, then your mean square error is going to going to perform well. But the problem is there are some problems where there are multiple minimas. Out of that, one would be a global minima. Similarly, there is a possibility that there could be multiple global minima. Okay, so wherever you have wherever you have multiple global minima scenario or global maximum scenario, in those scenarios your mean square error will fail. Okay. So these are just four challenges that we normally face when you use any when you design any algorithm based on the mean square error as the criteria. Okay. So to tackle all these four challenges, there have been a lot of research on the robust cost functions that could be used instead of error square. Okay. So there are many cost functions which have been listed below: LMP, information theoretic cost functions, logarithmic cost functions, rank-based cost functions, okay, zero attracting cost functions. So there are survey articles. One of the articles is listed below. So you can go through those cost functions, and effectively the idea behind designing these cost functions is to tackle all these four problems. Okay, but then when you look at all these cost functions, you will see that when you are designing, when you are using a cost function for designing any algorithm, you might be able to satisfy few of these criteria. You might be able to design some algorithm which is very good in terms of its robustness to outliers, but not necessary that that algorithm is going to be very very good when it comes to correlated noise. Okay, so there is a trade-off between all these the performance in different environments, whether outliers, whether correlated noise, or whether non-Gaussian noise. Okay, so based on the trade-off, you can compare all these cost functions, and uh, depending on what is your requirement, because there are some applications where the sensitivity to outliers is very paramount. So in that case, my objective is more tuned towards the first challenge. Okay. Similarly, there are few applications where the correlated noise creates a big problem. So in those scenarios, you can use a norm which is more focused toward handling the correlated noise than handling the outliers. Okay, so based on the application, you can choose a particular cost function. So I have listed all these cost functions in this table. Okay, that has been taken from the previous survey article. Okay, in the footnote, the reference for the survey article is listed. So the approach, how they use the cost function, what are the different advantages, what are the different disadvantages, and you can see in the disadvantage column, you'll see that there are few cost functions which are very complex. There are few cost functions which are very sensitive to noise, right? There are few cost functions which require lots of tuning of parameters. Okay? So each has some pros and cons. So based on the requirement as far as the application is concerned, which is listed in the last column, based on the requirement, you can choose corresponding cost function. Okay? Now, among these cost functions, now the second row corresponds to information theoretic based cost functions. Okay, and if you look at the second row, the approach is based on minimizing some information theoretic measure. Information theory links to your entropy, core entropy measures. Okay, so you can use any of these information theoretic measures to design the cost function. And if you look at the advantages, these are very good in terms of handling of non-Gaussian noise, in terms of handling of outliers. Okay, but the limitation or the disadvantages, these are very computationally intensive. Okay, so wherever you do not have any restriction as far as the computational resources are concerned, in those scenarios, you could go ahead with your IT or information theory based cost functions. And you can see the applications, for example, robust estimation, machine learning, communications, uh, where you do not have any constraint on computational resources. For example, machine learning, we normally use lots of GPUs, lots of computational power. So in that scenario, I can easily use information theoretic based cost functions to design no, to design the algorithm. So I'm going to talk a little bit more about this information theoretic divergence. So the first similarity measure, or you can say it's a dissimilarity measure. Uh, so in this case, what happens is when you look at the adaptive filtering problem, we talked about two things. One is the desired signal, and the other one is your estimated signal. So what we do is we want our estimated signal to be as close as possible to the desired signal. So that is the reason that we were calculating the error and then we were taking error square. Now that was a sample to sample difference. Okay, so we were calculating the difference between two samples of desired signal and estimated signal, right? Now, this information theoretic divergence, what it does is instead of looking at the samples of the signal as individual values, what it does is it looks at the complete signal in terms of the probability distribution. So, say for example, my input follows a Gaussian distribution, and my desired also follows a Gaussian distribution. What information theoretic divergence does is finds the distance between these two distribution functions. Okay, not individual samples, but the two distribution functions. So the individual samples might be very close to each other. So let's say out of 100 samples, there could be two samples which are very close to each other as far as the desired and estimated are concerned. But there is a possibility that the overall distribution of those 100 samples of your desired signal and estimated signal could be, could be varying by a big margin. Okay, so the difference between those two distributions could be a big margin. Okay, so that is the reason that this particular approach is mainly focused at the probability distribution function, not individual sample values that we conventionally use to calculate the error or error square. So the divergence criterion, what it does, it finds the distance between two n-dimensional probability distribution functions. Let's say p and q in bold letters. Let's say these variables represent the two distribution functions, and the non-negative measures, so it's a positive measure. Okay, it measures the quasi distance or the distance between two PDFs. So the non-negative measures, it's not normalized to one. So we do not know, because you have taken only, let's say, 100 samples out of the complete signal. Okay, so it's not necessary that those 100 samples will form a PDF which would ensure that summation of pi is equal to 1. Okay, but it satisfies certain criterion. For example, when you look at the measure that is written in terms of the italic D, capital D, so what we can see is, what we can say is that the summation of the distance between pi and qi, that is greater than equals to 0. And this will only be 0 only when both P and Q are exactly similar distributions. So when P is equal to Q, then only this summation of D of Pi Qi is equals to 0. Otherwise, in all other cases, the difference would be positive. And it's not necessary that the distance that you have calculated between the two distributions P and Q, when you calculate the distance from P to Q, and when you calculate the distance from Q to P, it's not necessarily they are symmetric in the sense that D of P's bar Q is equals to D of Q bar P. So it's not necessarily symmetric in this sense. Okay, it is it could be asymmetric, it could be symmetric, but it's not mandatorily symmetric. It doesn't necessarily satisfy the triangular inequality. Say, for example, we have another distribution which is Z. So it's not necessary that the distance that we are measuring between the two distribution functions P and Q would be less than equals to the distance that we calculate between P and Z and Q. Okay, so it's not necessary that the triangular inequality would be maintained. Why I am showing all this, all these equations is, if you compare this cost function with that of your error, because let's say when you calculate the error, your P minus Q whole square is same as Q minus P whole square, right? Because if you look at the difference, you're squaring it up, the value is same, but this is not true in this case. So it's not necessary that the distance measure will remain same when you flip the variables. Okay. So there are lots of information theoretic divergence measures based on which you can design the adaptive filtering adaptive filter. And the broad categories are Sieger's divergence, Bregmann's divergence, alpha divergence, beta divergence, gamma divergence. This is just a list for you to have an overview of the information theoretic divergence measure. Not necessary that you have to go through every divergence criterion and check it. Okay? But I'll be focusing on one or two of them, so that you have a basic idea of how the divergence criterion is used. Which one to use, that you could decide based on your application. What kind of computation complexity your application can manage, what kind of uh, time, computational time that the application can manage. So based on that, you can decide some divergence measure for the application. Among all these divergence measures, the first one is your Caesar divergence. The Caesar divergence is simply defined as summation of qx into some function of ratio of px and qx. Okay, p and q are the two distribution functions that we talked about. Okay. Now, why this divergence is so popular? It unifies multiple divergence measures. Means, a lot of divergence measures can be found out from the single divergence measure, which is Caesar's divergence. Okay. Uh, the, some properties of the divergence cost function which are helpful as far as the mathematical analysis is concerned. So those are listed below. That is convexity, duality, and data processing inequality. So when we look at the seizure divergence measures, as I said, this cost function that you see in this slide, this could be generalized to get multiple kinds of divergence cost functions. Okay. So those are listed in the first column. For example, Pearson distance, Neyman distance, triangular discrimination, all this could be found out from the same formula where F is specified in the second column and the divergence measure is specified in the third column. Okay, so based on as I said, the complexity of some of the measures might be very high. Okay, but then the accuracy achieved is very good. So you have to take a call based on the requirements of your application. This is just a no, figure showing that if you vary one of the probability density functions q, what would happen to the divergence measure? So, for example, you can see that there are some divergence measures. For example, your total variance distance, you can see it has a null at zero point 0.5, and it's more like a triangular scenario, right? Similarly, when you look at the Pearson's distance or Neyman distance, if you go on increasing the PDF, no, the Q, then what is happening to the divergence measure? It spreads out. Okay. Now, the divergence measures are compared in terms of how they are getting spread out over when we go away from the optimal point. Okay, so the Gaussian function is the conventional one that when we go away from the mean value, it gets spread out, right? So sigma, 2 sigma, 3 sigma, all those are defined based on how the Gaussian function is being spread out, right? So similarly here also, when you go to the left or right side of the optimal point, how this divergence measure is getting spread out, that is what is shown in this particular graph. So as I said, it's not necessary that you will always have this symmetricity in this divergence measure, which was there in the error square case. Error square case, p minus q whole square is same as your q minus p whole square, which is not true in this case. So there are two versions over here. One is the symmetric divergence, where that is maintained. So while the standard divergence is asymmetric in nature, a symmetric form can be obtained by taking the mean of the two. Okay, so you can take the mean of the divergence measure. So the mean is from p to q. Now the divergence measure of p to q and divergence measure from q to p combined together, you can have the symmetric form. Okay, so the symmetric form can be obtained from the asymmetric forms, but then you have to calculate both the asymmetric forms and then find out the symmetric form. Uh, why use symmetric divergence? We know when you look at the error square cost function, your p minus q whole square is same as q minus p whole square, and there we feel that whether my error is +5 or -5, it doesn't matter because I'm 5 away from the optimal point, right? So that is the reason that we were more interested in a symmetric cost function where +5 square and -5 square gives you the same value, and that is the conventional notion. Okay, so if you want to go for symmetric one, you can of course design a symmetric counterpart of this asymmetric Caesar divergence. So if you do that, there are symmetric counterparts corresponding to the previous table that I had shown. So these are the symmetric counterparts for them. So these are the cost functions when these asymmetric counterparts are converted to symmetric ones. So you can now see the graph for symmetric divergence measures. Similarly, there is another category of divergence which are called as Bregman divergence, and if you go back to the previous case, the divergence was linked to the ratio of the two PDFs, Px and Qx. Okay, so the function f was linked to the ratio of Px and Qx. Now, if you look at the Bregman divergence, again, this is linked to the gradient of one of the PDFs. Okay, so if you go back to the error square concept, the error square concept was taken up because we had a continuous derivative, right? So the gradient was also used while designing the mean square error cost function, where you finally get something called as least mean square algorithm, right? And that was based on your steepest gradient, steepest descent approach. So where the gradient is involved. So here also in this Bregman divergence, the gradient comes into picture. So we look at the gradient of the PDF, let's say the gradient of the Q, and the gradient is obtained for a convex function of x. Okay, so we can see the gradient coming into picture similar to what you had in the error square scenario. And this Bregman divergence is useful uh, in because of its because of the involvement of the gradient, that is for sure. And this is also useful in non-probablitic settings. For example, where unlike your KL divergence, which requires probability distributions, here if you, in case you do not know the exact distributions of P and Q, even if you approximate them and use it for Bregman divergence, then also the cost function performs very well. Okay? So that is the reason that for non-probabilistic settings also, you'll see that the Bregman divergence also performs well. So again, a list of Bregman divergence measures. Okay. The plots, similar plots for your Bregman divergence. Again, asymmetric alpha divergence, symmetric alpha divergence. Okay, so the complete set of cost functions that I had listed here, those have been shown in brief in the subsequent slides. But I'll just quickly go to the applications part. So alpha divergence, beta divergence. So every divergence has a symmetric and a asymmetric counterpart, unlike your error square. So remember that error square was a symmetric scenario, whereas your divergence measures are uh, in general asymmetric and could be made a symmetric one by some modifications. Okay. So similarly, gamma divergence. Okay. So now let's look at the applications. Okay. So as I said, you can get the divergence measures from the articles that have been published in IEEE, or you can also get information theoretic divergence or information theoretic cost function related books where all these are listed. Okay. But let's look at the applications which is more interesting from the artisanal processing point of view. Okay. So the first application that we are going to deal with is system modification, where we are looking at different kinds of systems. So the system could be static system, means my transfer function of the system is a fixed one, okay, or the transfer function of the system could be varying in nature, that is time varying system, or error in variable, means there is some error in the system transfer function, or there is some error in the input side which could also be brought into the system, okay? Or you're dealing with a non-Gaussian noise. Okay, so we listed few of the challenges that we normally face while dealing with error square cost function. We'll see how the information theoretic divergence cost functions help us in in dealing with those challenges. And some more applications are adaptive noise filtering, adaptive line enhancement, sensor modeling, distributed estimation. So I'll just have a quick overlook of all these applications. Okay. Now on the left side, we have a block diagram where the system identification is shown, and this is a conventional system identification using adaptive filter. So on the top, you have an unknown system H naught, and you have an adaptive system HI, and the input is x of I, and the desired is zeta I, and you can you can find out the error between your adaptive system output and y of I. Uh, your sorry, in this case, your zeta I is shown as a noise, and your desired is y of I. So you can find out the error and use some adaptive algorithm to update the adaptive system parameters. Now, so far you have been taught about lots of algorithms, evolutionary algorithms, right? Particle swarm optimization, genetic algorithm, multi-objective algorithms. All those algorithms can be used as adaptive algorithm. So all those algorithms can also be used here. Okay, but instead of using all those evolutionary algorithms, we are going to talk about a counterpart of the least mean squares algorithm. Okay, which is based on your information theoretic divergence. Okay, but all those evolutionary algorithms can also be used as adaptive algorithms in this particular block. Okay, now uh, on in the second figure, what is shown is your mean square deviation between the unknown system weight h naught and the adaptive system weights hi. So what is the difference? So h naught minus h of I, that is shown in the second figure, and you can see that the various variants of least mean square algorithms have been shown in this particular graph. Okay, these are all information theoretic divergence based algorithms. Only the conventional algorithms are least mean square algorithm and the block least mean square algorithm. So the LMS and BLMS, these are the conventional ones. Rest three are based on your information theoretic divergence. Okay, so we can see how these algorithms are behaving over time, and the mean square deviation is decreasing over time. Okay. Uh, Now, when we started the discussion on information theory divergence, we said that the conventional error square cost function uh, performs poorly when it comes to outliers. Okay. Now, the third graph shows the performance of these algorithms when outliers are there. Okay, and if you look at the least mean squares algorithm, you'll see that the performance of the least mean square algorithm is degrading because of the outliers. Okay, so the green color one, you can see that it has the performance degrades because of the outliers. Okay, but when you look at all these information theoretic divergence criterion based algorithms, these could be easily fine tuned to work in presence of outliers. Okay, so here you can see that the filters have been tuned looking at different application. Okay, but you'll see that the parameters can be tuned to make sure that the algorithm performs well in presence of outliers. Okay, so this is how the system adaptation problem can be dealt with using information theoretic divergence based adaptive filters. Second one is again time varying system modification, where again, if you look at the previous figure was H naught. There was no N in the block. In the top block, there was no N. But right now, if you look at the top block, you have W naught N. So that's a time varying unknown system. Okay, because the system parameters are changing over time. And again, you use similar kind of approach to solve this problem. And the performance of various algorithms in presence of Gaussian noise and in presence of outliers are shown. Okay. So these are comparisons of some of the state-of-the-art algorithms when outliers are faced with different noise powers. So point one is low noise power, and similarly, what kind of signal power you have. You can go on varying those signal power and noise power and check how the criterion is behaving. Okay. Again, as far as the noise is concerned, either the noise could be Gaussian distributed, could have exponential Laplacian distribution. So there are some mechanical systems where you find Laplacian noise instead of Gaussian noise. So how the algorithms perform in those systems, that also can be checked. The second application is your adaptive noise filtering, and here you can see that the input SI goes into the goes as the desired signal, and let's say some errand, some noisy signal S tilde I goes into the adaptive system. So the error epsilon I is used to update the adaptive system parameters. And again, these adaptive algorithms could be any one out of the evolutionary algorithms, or it could be any one based on the LMS uh, counterparts. There are many LMS counterparts which could be used. Okay, and here we are just comparing all the information theoretic divergence based adaptive algorithms. Okay, it's not necessary that you have to use only information theoretic divergence based algorithms. As I had shown in the beginning slides, there could be different cost functions based on the application requirement. Similarly, the third application is your adaptive line enhancement, where we would like to enhance the signal which is buried under noise. So the noise part is nu of n. So S of n is getting added with nu of n, and you have a noise, noisy signal. And this noisy signal is used at the desired one, as well as delayed noisy signal is passed to the adaptive filter as an input, and we calculate the error and update the adaptive filter weights, and we see that the information theoretic divergence based algorithms can also be used to tackle adaptive line enhancement problems, where the signal S of n is buried under large noise. Okay. So you want to recover the original signal. So your signal S of n is a low amplitude signal, low power signal, which is buried under noise. Okay. This is another example of target tracking, and this is the missile trajectory is shown, and the starting point and the ending point is shown, and the pink color lines show how the algorithm is able to track the object. And if you use any of these information theoretic divergence, then you can also track the object. Okay, and here the beta divergence has been used to track this object, and the pink color graph shows that when the object reaches the ending point, you should be able to predict the ending point position beforehand. Okay, so that is what the target tracking is aimed at. So these algorithms can be used to predict the position of uh, these objects, and the green color star marks show the endpoints of all these objects. Okay, so if you are able to track them correctly, then the suitable measures can be taken to handle those objects. Similarly, another application is your high cost sensor modeling. Say, so what we did was we had a high cost temperature sensor and we had a low cost sensor. And let's say you do not want high cost and temperature sensors to be used in a large number, and you want it to be replaced by low cost sensors. So your DST11 is a very low cost temperature sensor, and BME 280 is a very high cost sensor. So BME 280 has been used to generate the desired signal YK, and YCAP K is coming from a low cost sensor, and we find out the error, that is delta of K, and we used beta LMS, which is nothing but beta divergence based LMS, to update the weights. Okay, so if the adaptive filter has been tuned very well, then in that case my DST11, which is a low cost sensor, along with the adaptive filter, will act as a high cost sensor. So any high cost sensor can be replaced by this low cost sensor plus adaptive filter block. Okay, so the DST11 with adaptive filter block can be replaced, no, can be used to act as a high cost sensor. Okay, so that is how the hardware setup has been done, and the modeling has been done. Similarly, distributed estimation over wireless sensor network. So let's say we have a wireless sensor network with 20 nodes. Then if you want to estimate the temperature over the complete region of interest, all sensor nodes can collaborate among themselves to to find out the average temperature of the area. in general, what happens is you get the value from each of the temperature sensors and you take the average of all these values to find out what is the average temperature of that area. But instead of getting temperature values from each of these sensors, what we can do is we can use distributed estimation. So that means each sensor will record the temperature, but then the let's say there are various strategies. Say for example, the simplest strategy is, let's say the sensor node 1, whatever temperature it has measured, it will pass this information to sensor 2. So sensor 2 has two information. One is its own information, own temperature information, and the other information that it is getting from sensor 1. Okay. So what sensor 2 would do is it will combine these two information and send the new information to sensor 3. So imagine if you go on doing this, when you reach the 20th sensor, the 20th sensor would be having information which has come from all the previous 19 sensors. Okay. So you don't require data from each of the sensors to be sent to the server. Rather, a particular flow of data can help you in estimating the temperature uh, with very simple topology. So the graphs for different kinds of noise that you can face in an environment is shown below. So, for example, if you face Gaussian noise, what would happen? If you face impulsive noise, means very very high value of noise for a small interval of time. So that is impulsive noise. And how the divergence based cost functions perform in those scenarios, that is shown in the below two graphs. Similarly, you can also use these divergence based cost functions for channel estimation. Again, channel estimation is very similar to your system identification. The system is now replaced by the channel. So the system transfer function is nothing but channel transfer function. And you can the previous case was estimation of system parameters. Now those system parameters are channel parameters, so effectively you are estimating the channel with some signal. Okay. Now for estimating these parameters, what we do in general wireless communication is you send some sets of pilot signals and you receive those pilot signals. Of course, these pilot signals will go through the channel, so there will be some attenuation, there will be some disturbances, there will be some noise added to the pilot signal. So when you receive those pilot signals at the receiver, to use this noisy pilot signals along with the original pilot pattern to estimate the channel. Okay. But there are some cases where the pilot signals are also limited in number, so those pilot signals can also be contaminated because of the interference that you get from multiple users. Okay, so in those scenarios also we have tested the divergence based cost functions, and the graphs are shown here. That divergence cost function, divergence criterion based cost functions can also be able to they are able to estimate the channels whenever the pilots are getting contaminated. Okay, so that is also a possible using your divergence criterion based cost functions. Okay, this is exactly same as your adaptive system identification problem, only the system is replaced by channel now. So the overall conclusion is you can look at the cost functions, and the traditional cost function is based on mean square error. But these mean square error based cost function, the they face multiple challenges. I had shown four challenges that we see. Outliers, correlated noise, non-Gaussian noise, right? So all those challenges are faced when we use mean square error as cost functions. So we replace this mean square error based cost functions by information theoretic divergence based cost functions, and we saw that these are very robust to outliers. These are also performing well in terms of non-Gaussian noise, in terms of correlated noise environments. Okay. And the information theoretic divergence based cost function can be chosen based on the application. So you have a diverse set of divergence measures, starting from Seeger's divergence to Bregman divergence to alpha, beta, gamma divergence. So you can choose any of these divergence cost functions. I had shown you the profile of all these divergence cost functions. So you can, based on the requirement, you can choose a certain cost function. Uh, as I said, it depends on the system characteristics. Okay, so some of them would perform better in low signal to noise ratio environments. Some will perform much better in structured or block based estimation scenarios. All of these divergence measures have their asymmetric uh, counterparts as well as symmetric counterparts. The conventional ones are asymmetric counterparts. Okay, understand that there is a difference between these error square cost function, which was a symmetric cost function, whereas your conventional information theoretic divergence measures are asymmetric in nature. You can find out a symmetric counterpart, but conventional ones are asymmetric in nature. So based on different settings, a particular divergence measure can be exploited as a cost function to optimize the adaptive filtering performance in specific applications. Okay. The aim was to just give you an overview of the divergence measures, because in general we look at the convergence of the algorithm, but here is a divergence measure which is used to make sure that the algorithm converges. Okay, so I hope everyone gets a brief overview of information theoretic divergence. You can go into details of all these measures, and there are a lot of articles which analyze these divergence measures in mathematical terms. So the divergence based cost functions provide enhanced robustness. Okay, I said non-Gaussian noise, outliers. You can look at all these challenges, and you will see that the divergence-based cost functions provide perform well. Different divergence measures can be used based on the application requirement. Asymmetric and symmetric counterparts are existing. Okay, and beta, alpha, and other divergence measures outperform mean square error in various adaptive filtering tasks. Okay. The appropriate divergence measures should be selected based on the system constraints. Okay, so as I said, there are some divergence measures which are very computationally complex. They will give very good results, but then the computational complexity is very, very high. So if there is no restriction on computational resources, then you can of course go ahead with those highly complex divergence measures. Uh, Future work, you can optimize the divergence based cost functions. You can have adaptive selection mechanism. So the way we optimize the parameters of the adaptive filter using evolutionary algorithms, you can also use those algorithms for optimization of these cost functions. Okay. There could be a hybrid divergence function which combines multiple divergence measures. Okay. The computational efficiency and real-time application can also be looked at. Okay. For example, as I said, if you look at all these divergence measures, those are a little bit more computational complex as compared to your error square cost function. Okay. So you can no, you can look at the computational complexity, you can reduce it, yeah, and you can also look at the parallel and hardware isolated implementations of all these information theoretic divergence based cost functions, so that the computational complexity can be brought down. You can generalize it to distributed learning. You can also use it for federated learning, which is a highly popular topic nowadays. And of course, you can design them for nonlinear system applications, other biomedical signal processing related applications, radar systems, autonomous navigation systems. I had shown one example of tracking, which is related to your navigation. Uh, of course, as far as the theoretical background of information theory is concerned, you can always work on that to advance the concept in divergence measures. Okay, so new divergence families and generalized cost functions, Bayesian information, entropy-based optimizations, reinforcement learnings can be used to design new divergence measures. So that's all from my side. Thank you very much. If anyone has any queries, please feel free to ask. Oh,
Good
so
evening.
Dr. Nanda is back.
Yeah, there was exam duty, so I was not there for some time.
Yeah, no problem.
So, participants, if you have any queries, you can write in the chat box to Dr. Pradhan.
Probably the concept is a little bit mathematical in nature, so
Yes, yes.
yeah, so it will take a little bit time to grasp
Yeah.
these things. But fine. Feel free to write to me through email if you have any queries related to
Yes.
this talk.
So, Dr. Pradhan, I will also request you to share the slide so that it will be.
Yeah, I'll just
Okay.
send it once the talk has come over. I'll send
Yes.
it.
Yes. So, Dr. Pradhan, I am very much thankful to you for delivering very two important session in this advanced optimization technique using MATLAB workshop. Actually, your contribution have been immense over the years to develop this particular workshop from a last decade, I can able to say. And this time, this advanced optimization technique almost it started with 2015, right? So this is
Yeah,
25, almost 10 years it has been
great.
there.
Yeah, yeah.
So we are very much thankful to you for your a decade of contribution, continuous over the years, years continuous support in this workshop.
Thank you very much. Thank you to you and the organizers that you are able to uh, manage this workshop over such a long time. Uh, this has been a good experience. Uh, Even we had some in-person activities before COVID. So it was great to interact with the participants in person and have their view related to our concepts. Sometimes we miss few things which the participants point out, so that makes it interesting. So yeah, thank you very much. Thank you to you, your organizing team, Dr. Sarma. So yeah, thank you to all the attendees. Have a nice time.
Thank you, Dr. Pradhan.
Okay,
Good night.
thank you.